Welcome to my channel. Today in this session, let us discuss about the time response of the second order system subjected to unit step. Already we have discussed about the response of first order system when it is subjected to the unit step. In this session, we are going to discuss about the second order system. Okay, and here R of t is equal to 1 and R of s is equal to 1 by s. This is towards the unit step input. That means the signal which changes state from one to another is given by R of t, which is equal to 1, and its domain S domain is given by 1 by s. This is for the subjected to the unit step. With this unit step input, I am going to analyze the response in the second order system. As discussed earlier, this is the standard form of the second order system, and in the standard form, we know about the R of s, which is equal to 1 by s. I am cross multiplying the R of s with the standard form equation of the second order and substituting R of s as 1 by s, I get C of s is equal to 1 by s into omega n square by s plus theta omega n square plus omega d square. Okay, this is already known. This is known with respect to this first order system also. Here, the only change is nothing but we are having a standard format of second order system. Okay, and in the standard form of the second order system, while discussing towards this equation, quadratic equation, we have solved and also found out the value was s plus theta omega n square by omega d square, right? This is already discussed while discussing the second order system. Okay, and what about the omega d? Damped frequency of oscillation omega d, which is equal to omega n square into 1 minus theta square. Natural frequency is omega n. Theta is the damping ratio. Okay. In this equation, I am going to substitute this omega n square into 1 minus theta square. Okay. And substituting and taking the partial fraction for 1 by s into omega n square divided by s plus omega n square, and in this term I have substituted as omega n square into minus theta square. I get the expression of C of s as s plus theta omega n square plus omega n square into 1 minus theta square minus s plus theta omega n square plus omega n square into theta square divided by this. Okay, so this is obtained by the partial fraction of this particular term, and already we have discussed about the partial fraction expressions also, how if we are going to take, right? And equating all those things once again in here, and we get in this half of the expression by breakup, we get the expression as 1 by s. Since the numerator term and denominator term of this part is equal and it gets cancels, and I have the expression as 1 by s minus s plus 2 s zeta omega n divided by s plus zeta omega n square plus omega n square into 1 minus zeta square. Okay. Okay. So this is the expression of S domain expression of C of S, right? And viewers, those who are thorough in the partial fraction, you just undergo the partial fraction and just check whether you are getting the C of S equation. And now once again putting omega d expression as omega n root of 1 minus zeta square, I get the expression this, and by taking the inverse Laplace transform, my time response of the second order system was. This is my time response for the second order system. Okay, this is obtained by the separation of these twos. That means I am finally getting this expression instead of 2 zeta omega n, I am considering as minus zeta omega n. So once again, I am taking the partial fraction and having the is minus zeta omega n, and I am tending the expression towards the inverse Laplace transform. While taking inverse Laplace transform for 1 by s, I get as 1. For this case, I get e power zeta omega n t cos omega dt. So Laplace transform for each and every function is already discussed in case of control system. So go through the video once again, and for this case I get e power minus zeta omega nt into sine omega dt. Okay, so by this I am taking the common terms outside and get the omega cos omega t plus zeta by 1 minus zeta what side zeta square into sine omega dt. So cross multiplying I get the expression as here this, and taking this term as common I get the time response of the equation for the second order system with the step input r of t is equal to 1 and r of s is equal to 1 by s. This is nothing but this is the expression, right? So with this expression, we need to analyze the time response, right? And for analyzing the time response, I am considering this case, and I have also plotted the response of the second order system with the input, step input, right? Here, in the expression, and I have the expression as already expression as 1 minus e power minus zeta omega n by 1 root of 1 minus zeta square into 1 minus root of 1 minus zeta square cos omega t plus zeta sin omega t plus t. This is my expression, right? And instead of root of 1 minus eta square, I am considering this as sine pi. That means I have taken this from the this right angle triangle. That means sine is nothing but opposite divided by the hypotenuse. Okay, zeta the damping ratio, and the opposite divided by hypotenuse, which is nothing but hypotenuse. Here I have 1. So root of 1 minus zeta square divided by 1, which is equal to pi. So the zeta and rate of 1 minus zeta square making an angle with the pi. So I am considering the term as sine pi, and for the sine cos phi, here this is zeta. Okay, and substituting the cos phi and sine phi there, I get the final expression as C of t, which is equal to 1 minus zeta omega square. So, so the expressions are very much important for the further calculations. So be thorough with the expressions of sine response, time response of expression with step input, ramp input, variable parabolic input for the second order system. Also the time response with the first order system for step, ramp and parabolic. Okay, and finally the error signal I get as e power minus t, e of t, which is equal to r of t minus e of t, and e of t, which is nothing but or e power minus sine omega t by root of 1 minus zeta square sine omega t plus pi. Since r of t is 1, this is already taken, right? So this one and this one will get cancelled. 1 minus 1, which is nothing but is 0. So we get the error signal with respect to this. This is the error signal expression with respect to this second order system. And the steady state value of this, or the steady state error of that second order system with the step input is, and for the time response steady state value will be equal to 1 and the steady state error will be 0. Okay, if it is 1, this will be equal to 0. And coming to the time response of the second order system, when it is subjected to unit step in signal, the plot is sinusoidal with exponentially decaying function. The time response is nothing but sinusoidal and it is exponentially decaying. A steady state, there is no steady state error. In steady state, there is no steady state error. That means this is provided by this expression. In steady state, the error is 0. So, while handling the second order system with the step input, the error will be 0, and the error is time response is nothing but an sinusoidally exponential function. So, this is very much important. Have keep in your mind, in steady state error, the time response of second order system with step input which is equal to 0, and also the time response is exponentially decaying. So in order to know about the time response of the second order system, so far we have evaluated all those things with respect to the standard form of the second order system. And another important thing relevant to the second order system, either it may be of any type of input, we need to remember is the damping ratio with respect to the time response. Zeta is the damping ratio. If zeta is less than 1, it time response presents the damped oscillation. This is very much important. So be thorough with these cases, right? And when it is 0, there will be an undamped oscillations. So when it is equal to 1, the time response will be critically damped. And when it is greater than 1, the time response will be over damped. So to check or verify that damping ratio, we have analyzed the second order system with, of time response with step input. And finally, with the analysis, we have concluded that the steady state error is nothing but which is 0 in the steady state value, and the time response is exponentially decaying. And with the time response exponentially decaying, the zeta, which is in the case of the standard form of the second order system, the time response, zeta, if it is less than unity, there will be a damped oscillation. If it is again equal to 0, there will be an undamped oscillation. If it is 1, there will be a critically oscillation. And if it is greater than 1, this will be an overdamped oscillation. So those who are viewing this video, you have to be thorough with the time response equation C of t, error equation E of t, and the concept of steady state error with respect to the time response, and also the damping ratio oscillations with respect to less than, greater than, or equal to. Okay. If you like this video, with this session, I stop the discussion here, and let me continue once again with the second order system in the next session. If you like this video, like, share and subscribe.